What do you think, Sydney? Should we get going? What did we said? 2:30.
Yeah.
Because I have to run at 3, but I told Julie it might be 3:15. So I think it'll work. Okay. Why don't we get started? We're going to go into the next session, and this is going to be very basic compared to what Frank told us about in some sense. In other ways, I think it's pretty subtle. So when we discussed about what we want to talk about in terms of systems engineering and engineering design, Sydney, Charlie, and I thought it would be good for you to have a session or a discussion on design processes. How do different organizations choose to go from idea or requirement all the way to a finished design? What are different ways to think about it? And what I'll do in this session is talk about, in particular, 2 models that are extremes. One is the spiral development, a rapid prototyping way of developing new products, new systems, and the other one is the waterfall model. And as I'll show you some examples of real product development processes in organizations, and you see that many of them are actually hybrids. And the choices you make there are really important for the outcomes. So one of the comments that was made here is acronyms. Lots of acronyms, and I don't think this is something we've really paid a lot of attention to. So we're going to try to be very explicit about acronyms, and it's something that in aerospace, if you grew up in this industry, it's in your blood. You learn, and acronyms are a way to shorten things, but it creates a jargon that makes it less accessible to a larger population, right? So I don't know if you've heard this joke, but there's 2 guys are crossing in the hallway, and so one of them is Frank. So I run into Frank. Frank asks me, "Hey, what are you doing, Ollie?" And I say, "Oh, we have all these acronyms floating around. We got to do something about it." So what are you doing? "Well, I'm part of the ACR now." I said, "Well, what's that?" That's the Acronym Reduction Committee. So it's really hard for us to do that. So we'll try to do a better job. So let me get very personal at the beginning of this session to just try to explain to you a little bit, how did I get into systems engineering? How was my passion for engineering design and systems engineering ignited? And basically, you've heard that I'm from Switzerland originally. Hometown is called Fribourg here. It's on the language border between the German and French-speaking part. Went to ETH Zurich, and then a company called Ruag Aerospace, and then the big jump across the Atlantic to now it's Boeing. Back then it was McDonnell Douglas in St. Louis, and eventually found my way to MIT. The reason I came over to the United States was the personal reason was that it was just getting too confining. Switzerland, if you've been there, is a beautiful country. It's got a lot of rules. It's almost too perfect, and I just needed to come to a place that had a lot of opportunities. So I want to talk to you about this experience and the reason I came here. And there's one thing wrong, big thing wrong with this picture. What's the biggest flaw on this graphic here? Yeah. So what if we showed them in the right proportions? What would it be roughly? No, smaller.
Rhode Island?
It's basically kind of like New Hampshire and Vermont. It's like 1/50th, right? So the surface area is way smaller. And this gets me to the next chart. This is an F-18 aircraft actually flying in the Alps. This one has U.S. markings, but that's immaterial right now. So when the Swiss Air Force decided to purchase 3 squadrons of F-18s, this is in the 90s, it did so because the F-18, you'd say, well, why would a landlocked country, alpine country, buy a Navy aircraft? Well, good question. The short answer is the F-18 has great life cycle properties. Very easy to maintain. Maintenance, maintainability is built in. So on average, an F-18 requires about 20 maintenance hours per flight hour. The old generation was like 60, like the F-4. So it has great life cycle properties, and that was really the big driver. But there was a problem, and every small country faces that problem. Israel, Singapore, is that because the country is so small, there's basically no cruise flight. You take off, and then you're flying maneuvers, you're pulling Gs, and then you're landing. The average duration of a mission in Switzerland is 45 minutes. The average mission duration for the Navy is like 90 minutes. You know, you take off from a carrier, you climb, you cruise, and during cruise flight, things are very benign. And so what matters here is how many load cycles per flight hour the structure will see. So the spectrum in Switzerland and other small countries is about 3 times as severe. That's the number of, you know, flexing cycles that your wings will see, your fuselage sees, and there's a phenomenon called metal fatigue, and that's a big deal. And the part of, this is a picture inside of the F-18. This is known as the central barrel section. This is sort of the heart of the structure, the fuselage. You see the wing attachment points. These are called the wing lugs. That's where the wings attach, where a lot of the shear loads and bending moment from the wing is transferred to the fuselage. You see the 2 engine ducts. This is where the rubber meets the road. So if you're flying an aircraft differently than it was designed, you're going to start to have small cracks, micro cracks that start at the highest concentration points, stress concentration points, and then those cracks can grow. And if they become unstable, your aircraft can break apart in mid-flight. And that's actually happened, for example, the F-15 is flown by a lot of National Guards. So in some sense, this is also an issue in the US, but more at the National Guard level. Some F-15s broke up in mid-flight, and the whole fleet was grounded, and the reason is metal fatigue. So one of the jobs we had was to avoid that problem and think about the whole aircraft. So this is a cross-section of the F-18. Think about the whole aircraft. So you've got, this is the single-seater version. You've got the radar system. You've got a lot of avionics, the engines back here. This is a lot of the subsystems, hydraulics, etc. To think about what are the things in this aircraft that you have to redesign ahead of time to avoid these problems, namely the problems with fatigue. And I'll just give you one example of a change that we had to make. That central barrel section of the aircraft that I showed you traditionally had been made out of aluminum. And aluminum is a great material. It has great strength. It's lightweight. It's easy to work with in manufacturing. But it doesn't have great fatigue life properties. So after some analysis, we decided to replace aluminum with titanium, right? And you remember last night we talked about, when Jeff was talking about the superconducting magnets, and we found out it's a titanium alloy. Titanium is a great material. It has great thermal properties. It has great fatigue properties. It doesn't propagate cracks very easily. The problem is it's expensive, and it's heavier. It's much heavier. It has a density of about 4,400 kilograms per cubic meter, versus aluminum, which is about 2,700. But we did decide to make that change. We made some other changes as well to get the aircraft's fatigue life to where it needed to be. The problem is that, as you can see, this is a complex system. So by making that change, now there's some other, and I'm showing this in green because it was a good thing, because it gave us what we wanted, better fatigue life, but then other things happened. Gross takeoff weight, so gross takeoff weight means the weight of the aircraft with the passenger, with the fuel, everything included, was increased, and that leads to a decrease in range. Another issue now is the center of gravity of the aircraft has been shifted. Not a lot, just by a couple inches, but shifting the center of gravity in a complex system like this is a big deal. You have to make sure you have pitch stability in all flight conditions. So this was a bit of a challenge. A bigger issue turned out to be that we've stiffened the fuselage. This change plus some others, and I'm showing this here with this line. Every structure, even a simple rod, has natural modes of vibration. So essentially, if you excite it, it will vibrate like the string on a violin. So stiffening usually leads to higher frequencies. These natural modes of vibration are now higher. That's usually a good thing. The problem is that in a fighter airplane, you have in the flight control software, when the pilot actuates the stick, you have some filters in the control software, some notch filters, because if you put in a step input into the aircraft, the energy at those natural modes of vibration could be destructive to the aircraft. So you have to reduce the energy at those frequencies. So the problem now is that we have flight control software, but now we've changed the properties structurally of the structure, and the software, the notch filters, are now misaligned with what they were. So we had to retune the notch filters in the flight controller. It's flight critical software, so it's like opening the box and the warranty is void. Even if you just change a few lines of code or a few parameters, you now have to retest and recertify the flight control software because you don't know what unintended consequences the change that you just made could have on other systems. So think about this. We started with just changing material inside here from aluminum to titanium, and then through this multiple step process have to do make changes to the software. And some of these things we thought about ahead of time, and some of them were surprises to us. And that's kind of the excitement. That's what got me excited in systems engineering, is try to be try to make this more of a science rather than an art. Also, a lot of issues in manufacturing. Aluminum and titanium are different materials. You need to use different drill bits, different fasteners. Everything basically has to be recertified. So I don't want to get into too much detail, but for me this was a transformational experience and a lot of lessons learned. Like, high-performance aircraft are extremely complex internally, just like spacecraft. You have avionics, propulsion, structures, everything is coupled, and if you want to make a change because you want to just change this part of the system, it's very likely that those changes are going to cascade and cause other things to have to be changed as well. I'm not sure that's as true in all fields on Earth. We could have a discussion. Is it true in, where's Larry? Is he here? Architecture, right? Buildings, right? If you change, it may be true as well in some buildings, in various products. This is a big deal. Changing requirements can have a ripple effect because everything is tightly coupled. The whole system is much more than the air vehicle. So this was another learning experience for me. I showed you a diagram of that aircraft, but that's not the whole system. In order for that system to deliver value, it takes logistics, spare parts, training of the operators, training of the pilots, simulators, and so forth. And then this here, people matter a lot. It isn't just about the physical thing that you're building, but I could show you a diagram of all the contracts that were involved, of the people building the aircraft, building subcomponents, providing spares, providing information and support, working across different countries, the different cultures and the incentives involved in that. That's part of the whole, that's part of the system too. So just a quick introduction into what got me interested in thinking about systems engineering and system design more deeply. So now I'll take a step back and just talk about very basic steps. How do you describe a design process? And here, and this is one of the reasons I unfortunately had to miss Larry's lecture. I was at a meeting for Unified Engineering. This is our sophomore class for aerospace engineers, where we basically get into connecting the disciplines and thinking about design in a more systematic way. So what we do in Unified is expose students to a way to think about design in a systematic way. And these 7 steps are the most basic way in which I know to describe the process of designing a system or a new product. So the first thing you need to do always is define requirements. You need to understand what the needs are and who your customer is and what are they going to do with your system. So Frank showed us the importance, for example, of whether you're operating in low Earth orbit, LEO, low Earth orbit, right? Or interstellar. You said the GCR is 3 times higher once you leave the heliosphere, essentially, right? So, and how long are you traveling? This would be an example of requirements. Once you define where you're operating, how long you're operating, how many crew members you have, you need to define that in order to have the requirements for radiation shielding. Unless you know that, you can't really design because you're not quite sure what you're designing for. The second point, and this is really the focus of this week, is you need to bring in creativity. You need to create and then choose a concept or fundamental concept. And Sydney is going to talk more about what that means. How do you define a concept in a functional sense? Once you've chosen a concept, you design, meaning you take the concept and you actually implement it to the point where there's some detail, there's some dimensions, you're choosing material. If you're implementing software, you're choosing, what kind of algorithm are you using, and et cetera, et cetera. You analyze the system. You're now taking the design and you're analyzing it to see whether or not it is meeting the requirements that you had defined. And assuming that goes well, you build a prototype. You got to build a prototype, test the prototype, and then you accept the final design. So now one of the tricky things here is that ideally, in an ideal world, you would just check off the boxes and do one step after the other, and you're done. But design, at least design of things that are challenging to do technologically, that are new, that we haven't done before, doesn't work that smoothly. What you have is you have feedback. You have iterations. So I put in 4 examples of iterations. And they're a little different colors, and they're a little different. So the solid iterations are the ones that, that in a sense are, involve sort of physical prototyping and are typically done. The dashed ones are the ones that you'd like to avoid. So think of the solid iterations as the ones that are very frequently done and sort of value added. The dashed ones are the ones that you'd like to avoid. So when Charlie this morning showed us the example of the X-33, the helium tank didn't work, wasn't feasible. When they tested the prototype, they were out of money and out of time to go back and change everything, right? That's how that relates. So what are some of these iterations? You analyze the system, and it's close to working, but not quite. You have to tweak the design. So you got to tweak the design and then reanalyze it. So you might iterate here. Maybe things look good all the way to testing, and then in testing the prototype, you discover something you didn't know, some phenomena or something that surprised you. Your electronics are overheating. You thought they weren't going to overheat, but now the heat loads are higher, or the external cooling isn't as much as you thought. You have to go and redesign. This loop here implies that you really did a good job. You think you picked a good concept, a good design, but the requirements don't look like they're feasible. You were perhaps overambitious in your requirements, and you have to go in and perhaps negotiate and perhaps relax some of the requirements. And then, of course, here, this is a bad one too, where you did everything right, you're testing your prototype, and you're coming to the conclusion that you picked the wrong concept. You have to really go back to the drawing board and start from scratch. Yes?
I was wondering when you say analyze and test as 2 different steps, I was wondering what the real essential difference between both of them was.
The difference is that step 4 is mainly analytical. So you're either doing a model on a math, either you're doing hand calculation, you're solving, a set of equations, or you wrote a computer program that simulates the system. You can go very deep there. And this means you have a physical prototype that you're now like a wind tunnel, wind tunnel experiments, or I think the testing with mice that you mentioned, those are good examples of actually testing with real things, because often you have surprises. And one of the things we'd like to do is, ideally, this testing of prototypes is confirmation of what you already knew. And then people might say, well, that was a waste. We already knew that. Well, it wasn't a waste because the prototype gave you more certainty. But many times prototypes surface things that weren't included in the mathematical model. Yes, please.
In the first part, uh, I'll give two different examples. One is, let's say you know the problem. It's like the aircraft is developing stress fractures, and fatigue, and that is pretty well known. How do I fix a known problem?
Mm-hmm.
The other case is where you say, well, I'm not really sure what the issues are. So I would think then, and I'm sure I'm not contradicting what you're thinking, but embedded in number one is also understanding the issues and understanding the parameters, because I think too often designers go off and design a problem that doesn't exist, or they design the wrong problem, and they come up with a solution that's making a problem, and rather than say let's design a chair, rather than let's design a support system that doesn't presuppose it's a chair, and that's kind of a dumb example.
No, I completely agree with you, and this is a big tension. Is how much time do you spend here? Really trying to define. This is a big issue at NASA, right? How deep down and detailed can you get in the requirements before you actually start building and trying things? But building and trying things consumes a lot of resources because, tooling's expensive, materials are expensive. So there's a real tension here between spending enough time up front to really make sure you're solving the right problem, you understand the problem, before you start building things and spending big bucks on prototypes. On the other hand, you can't really discover everything up front without doing more detailed work.
But I think if I might just add one other thing, I think there's kind of a philosophical question here behind this, which strikes at the whole notion of innovation. Some people are very comfortable where someone says, okay, give me a problem to solve, and I'll give you a pink one that has one less gear or something. It's widget-centered, and it presupposes someone's going to bound the problem, establish the parameters, define the requirements. And then there's the other approach, which is the problem seeker. I'm not saying these are mutually exclusive, but the notion is that you find things that aren't working, and you say, here's an opportunity for invention. I'm looking at the way people do things, and my gosh, that looks awkward, or my gosh, that looks expensive, and you start challenging conventional notions about what something is, and you come up with something you see advertised on television on one of these programs. You get two of them for $29. But that's another, I think, aspect of innovation where it's a problem seeking as well as a problem definition process.
Yeah.
Yeah, I was just going to reinforce some of the comments made here. A lesson learned from Space Station, that first step where you're defining requirements, you should also, and this is, I guess, relative to the working with students, make sure that when you're defining the requirement, you're also defining a verification statement to go along and a method to verify that. Sometimes that's modeling, sometimes that's prototyping, because what happens if you don't do that properly, that's where those dashed lines come in. And a lot of people forget. They're too busy defining the requirements, which is a good step. But you also need to define a valid verification statement along with that to make sure that you know what you need to do to meet that requirement.
Okay.
So and we learned that in Station in many ways.
Good.
Yeah.
So let me move forward, and then we'll have some time for more in-depth discussion. So with the unified students, one of the first things we do is we have them build gliders, balsa wood gliders. Right now they're at MIT, and they think they're hot stuff, and this is a very humbling experience for them. Right, designing actually, and then we fly them for time of flight and distance. And they have great ideas, on bike. So this is just a sample out of about 70 different balsa gliders: a flying wing, a monoplane, a biplane, the Delta Dart. They get to name their own. And then we ask them to make an engineering drawing, and they actually have to put then the drawing and the assembly instructions into an envelope with a white envelope, and then it gets put into a basket, and then you have to go and pull out a balsa glider that somebody else designed. So you learn about engineering communication, and it's a fun exercise. But that's the first time they really get to think about design, documentation, and then iteration. It's very humbling to really design a good balsa glider. The other thing I talk about, and this is in the context of the balsa glider, is this is a very important distinction to be made between the design space, the parameters of the problem, and then the objective space. This is very basic, but I think it's crucial that the students really understand this. So the design space fundamentally describes, you can think of it as the knobs that you can turn in the design. So this is, as a designer, these are the things, choosing the concept, in fact, determines what the knobs are, right? And then, so for example, here we have wing area. You can change the aspect ratio, which is, whether you're going to have short stubby or long skinny wings. The dihedral angle is whether the wings are straight out or whether they have an angle with respect to the horizontal. Those are things that you as a designer can choose. It's within your control. Here are, and on the right side this is what we care about. This is what we want to achieve, performance at some cost. So time of flight and distance flown. Those are the two big objectives we're trying to achieve here, and typically we want to maximize those. Cost, it's primarily time, assembly time, and material costs that we care about. And then we have fixed parameters. These are things that they influence the performance, but we can't choose them as a designer. They're given by nature, by physics, right? So in this case, the air density, and then the properties of the balsa wood. The density, and balsa wood is anisotropic. Those are things you can't really influence. So we start talking and thinking about that. Last time when we taught this class so we did the icebreaker yesterday, your wonderful advertisements are why we should go to Mars. We did a slightly different icebreaker at Penn State. We started out with this egg dropping exercise, right? And I'll show you very quickly, we took some high-speed videos of that. But we gave the teams eggs, we gave them some very basic materials and then higher and higher drop height to make, design basically a load attenuation system. And so this is one of the examples. And it's the same thing. You're going through the same thought process. You have design variables. So if you look at this concept here, their concept was cross-strapping or separating the eggs through rubber bands. You have how many rubber bands are you going to use, right? Fewer or more. There may be an optimum. What's the right egg-to-egg separation? If the eggs are right on top of each other, then perhaps both are going to break together. If you put them really far apart, they're going to get, the containers were given. Everybody had to use the same container. So that was, if you put them close to the walls, that may not be ideal either. How many layers of bubble wrap are you going to use, right? Those are decisions you can make as a designer. Again, fixed parameters, air density, drop height, Earth's gravity, you can't really influence. And then constraints. These are things, parameters within which you have to operate. The container itself, no external modifications, and then how much time. And of course, don't break an egg. You could also argue that this is an objective or a performance. Peak acceleration, the maximum stress on the eggs, and then the assembly time and material costs. Those were the objective space. So let me just show you very quickly. It was quite okay. This is great footage that was taken here. We had one of Charlie's colleagues. So you can see here the drop height. Team 1, round 1, drop height. This was not a good one. And what was the outcome? So different teams tried different things. So that was pretty successful with cotton balls, with they try to see that's a parachute. So we had a lot of fun here. Just trying to basically achieve the performance outcomes using different concepts and then different design implementations, right? We can post this. This is I'm going to keep going here, but even an icebreaker exercise like that is essentially doing this process. Now, when you get into organizations and you formalize this, we talk about design phases, not just design steps. And so typically you have a conceptual design phase. That's where you decide on the general arrangement, representative configurations, the internal layout of your system. In preliminary design, you do more detailed analysis. You decompose the problem. Maybe you do some multidisciplinary optimization. And then typically detailed design means you're now implementing the design to a level of detail where you can hand somebody a blueprint and say, go build this, right? So you have essentially something that is known as a production baseline. It's now detailed enough so you can hand it to somebody and say, go build this. So that's and the reason we call this a waterfall process, because in some sense you can think about water flowing right through these steps, and it's like a waterfall, and it just keeps flowing down until you have a design that's done and that you can build. And I'd like to talk about this waterfall versus spiral processes. So this gets a little bit to what Larry was talking about, the philosophy of design. So one philosophy, and this is sort of the incumbent, if you want to call it that, has been this process here. Very much a waterfall, a linear process where you do product planning, product definition. This is where a lot of the requirements come in. Slightly different names: system level design, detailed design, integration and test. You launch your product. And the idea is that as you only transition to the next phase when all the work is done, when you've done everything, all the requirements are defined, right? The whole configuration has been determined. Only then are you allowed to go to the next phase. Spiral is a little different. Spiral, basically the idea is you're going to go through all these steps very quickly initially, and perhaps you're not going to do it it's not going to have all the features, it's not going to have all the bells and whistles. Maybe you're only trying to achieve 3 out of your 10 key requirements in the first spiral. So you're trying to get very quickly through the whole process, but it's incomplete, right? It's incomplete. But by doing that, you're going to learn a lot. You're going to learn a lot. You're going to break things. I think this is very much in line with the philosophy of this program. And then you go to the next spiral, and now you're going to pick up maybe the next 3 requirements. You're going to build in what you've learned in the previous spiral, and you do this essentially until it's time to launch your product. So that's a different model, and the big questions are, how many of these spirals should you do? Which are the phases? Because you might not have to do all the phases in each spiral. And gate reviews, that means at some point you have to show your design. There's somebody who's going to look at your design and say, okay, you've shown us enough, we're satisfied with what you've done, we're going to give you another $2 million or $200 million to go to the next phase. That's a very important part of design, is that you have some external, like Charlie said this morning, your baby, your design is your baby. You get very attached to it, and if your baby has some blemishes, you don't want to hear that. Well, you do need to hear it, and the role of these gate reviews is to do that. So, getting back to this waterfall process, often we show these gates with this diamond symbol. That's a milestone. That's how we designate milestones. And the idea is that you can only go to the next phase here if you successfully pass that review. If not, then you have to go back up and you have to iterate, and those are the unplanned iterations that we have talked about. So here's a visual, typically how the spiral process is. It's a way to show the spiral process. There's another way that I'll show you. And so in spiral, we're going to go through conceptual design, so planning, conceptual design, system level, detailed design, integration and testing, and then here the release. And you always start the spiral from the center, okay? So you see that the spirals are kind of small, meaning that the pathway here for doing a full, going through all these steps is pretty short. So we're going to do this very quickly. And then in the second spiral, and then we're going to have a review at the end of spiral 1. And then the second spiral is a little bit more comprehensive, so it takes a little longer to do. So we do this until we're ready to release the product. So the rapid prototyping, the idea of doing this quickly, using maybe not the final materials, but using a substitute material is exactly that process.
You know, Ollie, I look at that. It almost looks like a building block approach. You start very small. Maybe you do multiple things simultaneously in that spiral, but it's very much a building block approach till you're coming up with almost a full-scale design at the end. Am I missing something, or is that?
You could do multiple spirals in parallel. I mean, you want to make sure that things fit together at the end, but no, that's right. So last night, Sidney showed you a version of this chart, and he had talked about the Orion airbag landing project, and he had done 3 spirals. Do you remember what the 3 spirals were? What was the focus of spiral 1?
It was an analogous material. It wasn't the exact material. It was looking at the peanuts.
It was using bean bags instead of airbags, but it had sort of the general configuration. What was spiral 2 about? Remember? Charlie? No. What was spiral 2 about?
The number of airbags?
Yeah, it's close. It was about the venting dynamics, right? So spiral 2 was a single airbag, but getting into a lot of depth on all the valve designs to make sure they wouldn't leak, right? So it's sort of retrenching to just a single airbag to really understand the airbag dynamics, design these butterfly valves to really work and be tight, right? And that was spiral 2, and then spiral 3 was the whole setup with multiple airbags, all of them with valves with the drop test article. And so that's the idea, is you don't wait until you have everything, but you try to do a spiral, get to a quote intermediate product, learn from it, and then you launch into the next spiral. That's fundamentally the approach. And this is just a different way of showing it. The point here is that you can do spirals that don't include all the steps. So you could do a spiral that does a computer model, but doesn't actually do a physical artifact. So you can see these are the streams of work that we have, and now we're going to work through the project by basically picking up multiple of these phases and doing different reviews until we're done. So there's a lot of possibilities here of how to organize a project or organize design. So I just want to give you quickly some examples from industry. This is from the NASA Systems Engineering Handbook. This is the official way that NASA does projects, right? You have a pre-phase A, concept studies, phase A, B, C, D, E, and F is new. F is sort of closeout at the end. You retire a system, you archive the data. But what does that look like? Is that more a waterfall? Is that more like a spiral? It's very much a waterfall. Now, that doesn't mean that you don't have iterations within each phase, but the basic idea is that these big milestones here, these key decision points, are the ones that drive the decision whether you're allowed to go to the next phase. That's essentially how programs are done at NASA. Not just at NASA, but other organizations that are building expensive things. So this is an example of the BP project's common major process. They have 5 phases: appraise, select, define, execute, and operate. And I'm not going to get into details here. And the idea is that you have to be comfortable with some amount of risk by going to the next phase. You can't have full certainty as to what's going to happen. And we saw, obviously, that in BP's case, they really screwed up in terms of managing risk in the Gulf of Mexico. But the idea is basically that as you go to the next phase, you see this is the risk curve. We talked a bit about risk. Frank talked about risk reduction in understanding the biological effects of radiation. So the idea is as you go to the next phase, that distribution gets narrower and narrower, and you're getting to more certainty as you go down the path. Here's a third example. I like this example. This is a little bit dated by now, but I think it's interesting. This is Xerox. These are multi-function office machines. In this case, you have a web-based interface. these machines can print, they can scan, they can do a bunch of stuff, and they call their process TTM, time to market. And what's interesting about it is, so it's basically also a waterfall process, but for the software, they follow a spiral model. The reason that this is a big deal for Xerox is that every 4 years, the Olympics are coming up in London. The printing industry also has their Olympics. It's a big trade show in Germany every 4 years called Drupa. So Drupa is where all the, so Canon, Xerox, HP, all the big manufacturers show up with their new machines, the new generation of machines at Drupa every 4 years. And it's not just, people walking around sipping champagne. People actually come with their checkbook and place orders for new machines. So you have to make that conference, that exhibit, and you have to be ready with your new machine. So the reason they do the spiraling is because there's a list of features that they would like to have in the next generation machine. And they prioritize, the top 10 features, the next 20, and they work on implementing these features in this spiral way. And as the deadline approaches, those features that look like there's not going to be enough time and resources to implement are basically going to be delayed until the next generation. So this is very important if you're very deadline driven, that you're very clear about what are the things that you segment the features in your design and hit them one spiral after the other, and that you're ready to say, okay, we're really coming up on this deadline. We can't do everything. We're stopping at this spiral, and these other features are not going to be part of the product. Now that requires what in order to be able to do that? Well, over time, yes. It requires modular thinking, right? Because if some of the features that you're now excluding that you're not going to get done are essential to the basic functioning of the whole system, then you have nothing, right? So you really have to be very careful in terms of including the key features of your product in the early iterations, in the early spirals, and then the things that come later are a little bit more like icing on the cake. It'd be great if we had this feature, but if we don't have it, the remainder of the system is still viable. And I think some of this thinking could be very helpful in aerospace, in spacecraft design. I think spacecraft and aircraft are often not like that. Basically, it's all or nothing. And that's one of the big challenges we have. Yes, Sven?
I think that was more my comment. There's this propensity for feature creep, which happens, and particularly when you have engineers involved, they're like, wouldn't it be cool if we did this as well? That's when you have to shoot the engineer and say, we need just right now the bare minimum, we need to get this product launched. So, and that in the aerospace industry and space systems, feature creep is one of the big problems with scoping out a project.
I think you're right, and it's interesting because we engineers often put the blame on the marketing people, right? Like it's the marketing people that are trying to shoehorn all these things, but we may be culprits too. Absolutely. So I'm going to wrap up here just for time, and we'll have a short discussion. I just want to get through this, and then we'll have a discussion. So the examples I showed you, no matter what your PDP product development process is, you're always going to have these features. You're going to try to meet your customer needs. You're going to have some discrete phases of development. There will be iterations, even if you don't want to. You'll have them. You'll have reviews or gates that you have to go through, and then an attempt to control the risks, the development risk. So, for example, segmenting the requirements by things that are absolutely essential versus things that are nice to have is one way to do that. There are other ways. But there's also key differences in different organizations, different approaches. So, what names people put on these phases and how many do they have? Is it a 5-phase? Is it a 7-phase process? The type of iterations, type of reviews, where does the customer get involved? Sometimes the customer is only involved once the thing is on the shelf to be bought, right? That's not necessarily a good thing. There are companies that are very good at bringing in customers quickly and frequently. And one of the advantages of spiral development and rapid prototyping is that at the end of every spiral, you have something to show, you have something to share. Your customer can come in and say, I like this, this doesn't make sense to me, and you can take that into account. Obviously, the complexity of the product, and then the types of risks that you're going to address. So, there's been quite a bit of scholarship on this as well here at MIT on understanding, trying to really make this, like I said, into a science and understanding what kind of design process makes sense for what situation. And so the way you would go about this is you would, for your project or your undertaking, you would establish a risk profile. So for example, is this technologically very challenging? So the problems we're tackling here this week, mitigation for space radiation and then ultra-efficient eclipse, which we're going to hear about, I would put this pretty high to the right side. These are very challenging technical risks or technical performance requirements because if they weren't, we would have solved it. Market user, this is maybe a little bit less relevant here, but the preferences of our customers, are they clear? Is there a lot of uncertainty there? Budget and schedule. Schedule, this is a big deal in many. So the 4-year Olympics of the printing industry is one way to think about it. But if you think about launching to Mars, what's the big schedule? What does launching to Mars have to do with schedule? The solar cycle is 11-year. There's another cycle. I don't know, Larry, if you talked about the orbital dynamics for going to Mars. So there's another cycle, shorter than 11 years. There's the political cycle, every 4 years or 8 years, yes. That's the 4-year, 8-year, but there's another one that's really important for. So what's the periodicity of launch windows to Mars? 26 months, 26, 27 months, right? So that's, and that happened actually to MSL, right? MSL was supposed to be launched on the last launch window. They missed it, and they had to wait 2 years, which they used that time for doing, improving the system, but that's a big deal. So without getting into too much detail here, but there's a lot of choices. How many iterations are you going to have across phases, inside of the phases? Are these iterations going to be planned and scheduled, or are you just going to get into the project and let them happen to you? The gate reviews, how rigid are those gate reviews? So if and I've been in reviews that sort of span that spectrum. So if you're on the right side here, it means it's less rigid. So the review is just a check-in. How are you doing? Is it progressing? And there's not a lot of consequence. It's more like a check-in. This means unless you meet this criteria, this, and this is done, we're not going to allow you to go to the next phase, and you won't get the budget to go build your flight prototype. Very rigid criteria. And then frequency, how often are you doing this? And one thing that I've heard at NASA, I was on an NRC committee a couple of years ago where we interviewed, we looked at about 70 flight missions at NASA, was that there was a sentiment that these reviews were getting very, very frequent. And it was sidetracking the engineers from actually doing useful work because all they were doing was preparing presentations for the next reviews. So there's a happy medium there. And then now this gets to sort of being a little more organized about it. You can think about the waterfall process, this traditional stage gate process in design as having these characteristics. It has zero interphase loops. It's very much planning oriented, rigid phase gates that are rigorously enforced, et cetera, et cetera. And then on the right side, we have the spiral process with unspecified number of iterations. We don't really know ahead of time. And this is an interesting, this particular analysis was done by a colleague of mine here, Steve Eppinger, at the Sloan School. And what he claims, and his colleagues, is that if you're dominated by technology risk, you should do more the waterfall process. And if you're dominated by market risk, in other words, you're not sure what your customers really want, then you should do more the spiral process. And so I was thinking about this as Charlie was presenting, because this is a little different, right? Charlie is saying, no, we should do spiral development, right? We should do learn and break things early because we have technology risk. And so the way I think about it is when you're really working on new ideas, breakthrough things technology-wise that where you don't have a lot of maturity, in fact, I think working over here also for managing technology risk is a good thing because you're going to push the technology that you have to the limit. You're going to break things. You're going to learn. Once the concepts have been proven or you know that a certain concept or idea is promising, then it makes sense to inject it into a more traditional, organized stage gate approach. So I think those things are not incompatible. But Charlie, I don't know if you agree with that.
I look at it slightly differently, Ali. I look at it like if when you have to work in the conceptual phase to come up with many potential solutions to problems, you're looking for something, maybe the problem you don't want a conventional solution for. You don't want an incremental improvement like the next generation airplane, where you have a very rigorous approach of how to go about doing it, but you're only going to get an incremental gain. When you're looking for something to do a revolutionary approach to solving a problem, or a problem that's of such epic proportions that it's monumental to solve, you want to try as many things as possible, and you want to mature those possible concepts as quickly as possible in order to solve the problem. So in some cases, you have to solve a tough problem. It could be, it's not only it's a very tough problem, but you have to do it very quickly. So you could roll the dice and select the problem quick, or you could try a lot of them.
No, but I think that happens over here, right, on the right end, on the right end of that spectrum.
Yeah.
Yes.
I think I agree with both of you that I think one of the circumstantial which approach you use is probably the hybrid in any case, but I think one of the downsides of the waterfall process is that you buy into a concept very quickly, and then there's a risk that it's not the right concept.
That's right.
I think there's another risk that once you buy into a concept, you're married to it, you defend it, you become invested in it, and you will do your darndest to make that square hole fit in, square peg fit in a round hole because you're invested in it, and the time clock's running. So you say, no, maybe if I get a bigger hammer, I can pound that peg in. With the spiral process, I think it also implies two things. One is that you can break some eggs early, and get the experience of breaking the eggs, and get into the process. You can look at which are the showstoppers, and you can spiral around the showstoppers and say, let's see if this solution is going to address the big problems before we get to the small ones. So you can, and also I think it gives you an opportunity to look at these as trade studies, where it's a multi spiral, and you're spiraling a lot of these concepts, and some of them may have commonalities, where you're looking at different iterations of a kind of common theme. But I think in some respects you're minimizing risk, that at the end, at the end game, you don't come up dry or with a project you can't sell.
No, that's right. And so that thinking, I think, to try different things quickly, it's more on the right end. So there's a spectrum here in product development processes between, more flexible, trying things quickly, learning as much as you can, and then on the left side, the bigger and the more complex. It's a kind of tough tension. The bigger and more complex things get, the more phased and careful and organized you have to be. So I'm getting the signal here from Charlie. We're at the end, but I just wanted to give you a little bit of a flavor for thinking about design. We're definitely our focus this week is on the early part of that process, conceptual design, a little bit of preliminary design, but making these choices, how many phase gates you're going to have, how many prototypes are you going to build, this is all really crucial, and this is why a lot of companies are spending a lot of time thinking about, and in essence, a lot of companies are constantly trying to improve and iterate their product development processes. But the key points here are spend enough time. This gets back to the 1%. Let's try to spend more than 1% on conceptual design because the downstream impact of those decisions are huge. And doing spirals, including cheap but valuable prototyping, is really a valuable activity.
Thank you, Ollie.
Okay.